direi che possiamo iniziare i nostri lavori. Grazie per essere intervenuti a questo importante convegno. Dal momento che il convegno è in inglese, e anche per cortesia nei confronti del nostro ospite d'onore, il professor Canters, continuerò, o meglio cercherò di continuare in inglese. The first article of the statute of the Turing Academy of Sciences states that the Academy aims to contribute to scientific progress, to promote scientific progress. Despite this, all of us know that the scientific knowledge isn't produced today any longer in academies, but in universities, in research centers, in laboratories, and so on. All places where experiments can be done that today research cannot do without. However, there's another kind of knowledge which doesn't depend so much on sheer experimentation. This knowledge takes place when researchers gather themselves and share the results of their studies. In this case, the value, the quality, the importance of this knowledge is increased by the many perspectives from which it originates. In light of this, academies are indeed the most appropriate place for this kind of knowledge, since interdisciplinarity is, or rather should be, their main purpose, their peculiar feature, their very proper calling. As to the specific topic of our conference, I have nothing to say about it. I can't say anything at all, because I am a poor scholar in the humanities, and this topic, your topic, is too far beyond my area of competence. Nevertheless, precisely as a humanist, I would like to begin this conference with a philosophical consideration. That is, with a reference to Blaise Pascal. Pascal's general philosophical stance is that human nature is incommensurable and therefore unknowable. To prove that, this is too much to prove, to show that, in order to show that, he maintains in his pensée that man is placed between two infinites. The infinitely large on one hand and the infinitely small on the other. Let's quickly consider the infinitely small that fits better for our conference. 16th and 17th scientists had made a great deal of discoveries with their microscopes. And thanks to these discoveries, Pascal was fully aware that the regression from the small to the smaller could have no end. hence, he wouldn't have been surprised had he heard that we can measure and study a particle of matter as small as the billionth part of a meter. But this doesn't mean, this wouldn't have meant for him that we can better know what reality is and what role man plays in this reality. On the contrary, that would have been for him simply one more evidence that there is no commensurable relationship between man and this nano-reality. The conclusion is always the same. That is, the eternal, unchangeable, unknowableness of human nature. And this is perhaps the greatest difference between philosophy and science. Philosophical problems are essentially always the same. And history of philosophy is, one could say, a great repertoire thereof, a great repertoire of these problems. Science, instead, always progresses, steadily, continuously progresses towards new frontiers. And what was impossible, what appeared impossible yesterday, is feasible today and perhaps obsolete tomorrow. I'm very confident that this conference, too, will produce an enhancement of knowledge, will take a small step forwards, albeit a nanometric one. And with certainty in my heart, I am pleased to wish you some hours of fruitful, intense, and pleasant work. And lastly, I apologize in advance if I have to leave the conference in a couple of hours, because I have another institutional commitment elsewhere. Thank you very much. I give now the floor to Amalia Bosia.
Okay, it's written on the paper, the director of the class of physical, mathematical, physical, and biological sciences. Okay. On behalf of my colleagues of the class, I would like to welcome all the speakers of the meeting, together with all participants. My brief comment on the, let's say, content of this meeting are the following. The research on new technologies and new biology will be presented in the two sessions as basic research and applied research, as you have seen. As far as the basic research is concerned, the lecture of Professor Canters from Leiden Institute of Physics is likely will likely deal with the measurements of electron transfer rates in biological molecules, in particular copper-containing enzymes, and with the recent advances in monitoring these electron transfer events at the single molecule level. As far as communication are concerned, we will hear about the modulation of neuronal excitability by nanoparticles, the detection of neuronal action potential and dopamine release by multifunctional biosensors, the recent developments in surface chemistry, nanobiointerfaces, cell biology, and particle and fibers toxicology. As far as the applied research is concerned, the lecture of Professor Benfenati from the Italian Institute of Technology and the University of Genova will likely deal with the clinical applications of nanoactuators. The relevance of this topic is evident from the definition of biological actuations, that is, physical stimulation techniques to control or change the cellular or molecular activities, which is a really very, very large and important topic. As far as communication on applied research are concerned, we will hear about a major problem like re-engineering nature for a sustainable world, really major problem, about the clicking together modular protein domains, a powerful tool for conferring specific functions to engineered biomaterials, about nanostructured surfaces that allow the imaging of different drugs in solid tumors, about the development of theranostic agents, which are so specific that can allow diagnostic information together with effective therapy. So that's really a very important field of knowledge. And finally, I will just cite the nanobubble for drug delivery, nanoparticle guided modulation of stem cells. So you can see this is really a very short glance on the whole day. No? And so it's also a very attractive program, and I hope you will find it both useful and stimulating. So I thank you for your attention.
Ladies and gentlemen and colleagues, I propose to start with the first session on basic research. I first would like to thank the president and the direttore of the classe for giving to Professor Lovisolo and I the possibility of organizing this day and giving me the honor to chair the first session on basic research and introduce the first speaker, Professor Canters from University of Leiden, whom I'm very grateful for having accepted the invitation. In particular, Professor Canters was my maestro and still is my mentor throughout the years, since the days I was in Leiden in the early 90s. And it is a real pleasure for me to introduce him, introduce a scientist with an international standing in his fields of research and beyond. Gerard started in Amsterdam as a biologist, and he moved to United States through a series of postdocs where he moved from biology to physics to chemistry. And he went back to Leiden in the Netherlands as a full professor of biochemistry. He retired a few years ago and is now still emeritus professor in the same university at the Leiden Institute of Physics and is emeritus professor of molecular biophysics. His contributions in the metalloproteins and the study of the details of metalloprotein and electron transfer is invaluable to the scientific community. Gerard is one of the first, if not the first scientist, that in the 80s, when side-directed mutagenesis was a very tricky method to introduce mutations in protein to study the structure-function effect on the function of metalloprotein, he was the first one to clone azurin, a metalloprotein, a copper protein, and since then we can say that basically we mutated nearly all different parts of the protein, and we know all the ins and outs of electron transfer. So it is a great honor that I have to introduce you Professor Canters, who is going to deliver an introductory lecture, plenary lecture on protein-mediated electron transfer as studied by optical techniques. Please, Gerard.
Good morning, ladies and gentlemen. Thank you for being here. And thank you especially to Professor Mori and Professor Bosia for inviting me here to speak to you, and especially also to Professor Gianfranco Gilardi and Professor Lovisolo for letting me talk here to you. It was for me very interesting to listen to Professor Mori. My father was a historian, and hearing Professor Mori talk about the importance of the humanities was touching for me. As scientists, we have a tendency to concentrate on the technicalities of our research and sometimes are not very reflective about the effects they may have on society. We get focused, and that gives us the most pleasure. And it is important to have the people from the humanities to remind us that our activities take place in a greater society and should be considered also with respect to the effects on society. So it was a very touching moment to listen to you. Now, it is especially interesting for me and a pleasure for me to be in Italy, because Italy is a country with an interesting and important history. It is also the country where the art is very important. And so I use that sometimes to encourage my students when they are a bit depressed about the task they have to get a PhD. So I tell them, listen, look at this example. And here it is. This is a young man, and he is quite alone, and the only thing he has when he has to confront a giant is a little pebble and no protection. And yet he is successful and gets lots of admiration, as you can see here. So take that as an example, and then they say, yeah, that's fine, but it is hundreds of years ago. And then I can fortunately say, listen, in modern day Italy, there are also Davids, young Davids, which take on giants. And that is in the next slide, if it works. Have you put in the...
Yes.
Is it in?
Gonna try.
It's not on, perhaps. Yeah. Okay, so I show them this picture of the next hero. It's this one here. And fortunately, they keep their clothes on. And I cite this as another example. But then they say, listen, this is not serious, Professor. You are not taking it seriously. And then I can tell them, okay, in Italy, it's possible that this is not perhaps very serious, but in Italy there is always the church nearby to remind us that not everything is frivolity. And this is a picture many years ago. This is the Pope, a famous painting by Velázquez, and this is only a few years after the conclusion of the process against Galileo. And I show this picture to remind the students that science can be a matter of life and death. And so they should be taking it seriously. And that is also what is the subject of my talk today. I'm talking about electron transfer, and that is also a matter of life and death. Here, electron transfer is the basis of a lot or near all life on Earth, because it's the process that provides us with energy. So, if we have a look at the reactions that often are distinguished by chemists, there are 5 classes. And there are synthesis and the reverse of that, decomposition. There is positive charge transfer and the counterpart, electron transfer, and there is exchange. Now this part here, this is the basis of nearly all life on Earth. There is a few organisms that rely on fermentation, and they derive their energy from decomposition, but this is the most important one. And to show you what an enormous effect electron transfer can have, and the energy it may produce, the following picture, which is from a very unfortunate accident in 1937, that is from an airship that has traversed the Atlantic Ocean a couple of times, and it was preparing to go back to Europe across the ocean, and it was late, and the following day it had to depart. The captain was a bit in a hurry, and he had to make maneuvers, and the ship was full of hydrogen, of course. And one of the operations probably ruptured one of the compartments where the hydrogen was stored, and when they moored onto the construction here, probably a spark started ignition of the hydrogen and the whole structure collapsed. So it's an enormous amount of energy that can be liberated in an electron transfer reaction. And the question is, how does nature harness this enormous amount of free energy to get it working in a stable manner to provide energy for a cell? And so here is the picture of the reaction. It is oxygen with hydrogen. You could call this an oxidation reaction, as I learned in high school. The oxygen oxidizes, or the hydrogen reduces. But you can also consider it under a more general term as electron transfer, where electrons travel from an electron-rich compound to electron-poor compound, in this case oxygen, and you get this. So, in general, electron transfer reactions mean there is a transfer in the electron from one place to another place. And the question is, how does nature affect this in a controlled manner? The electrons have to run from one place to another, and they have to run in a controlled manner. Now, if we want to let electrons run from a high to a lower potential, the thing we do is we take a copper wire and connect the two, and the electrons start running. That's not possible in a cell. Nature cannot make metal threads in a cell to let electrons run. The cell consists mostly of water. So it's a non-conducting medium. And if you have open reaction centers, you get immediately short circuits. So how does nature take care of the electron transfer reaction in a controlled manner? And that is in the next picture. We employ metal wires through which the electrons run through conduction bands. But in the cell, the water prevents the doing that, and we have the risk of short circuiting. So the nature solution is we have redox centers that can store electrons, and we wrap them in a protein sheet that isolates. And then the electrons, we make it such that the electrons may hop from one center to the other center. A very known example is here part of the electron transfer chain of mitochondria, which are the factories that make the energy in a cell. And we see here how the electrons run from an electron-rich compound to water, to oxygen. The oxygen is converted to water, and the NADH is converted to NAD+. And what you see here is that the electrons are transferred from here to there in steps. This is the first step. Electrons go to a quinol, that is a small compound that acts as a shuttle for the electrons. They are shuttled to the next complex, and then they go to a protein that is usually drifting around in the solution, but it may associate with the membrane and affect the electron transfer from this complex to this complex where it is finally converted, helps convert oxygen to water. The important thing to notice here is that in each step a little bit of free energy gets lost and is used to transfer protons from inside to outside. So the electron transfer process is used to create a proton gradient that can be used for further chemical conversions. Now the question is, how does the electron transfer inside a protein occur? And that's what my talk will be about. And I will choose a compound that looks like this compound here in the sense that it is a soluble protein, that it is able to transfer electrons from one place in the cell to another place. The only difference is that it doesn't contain a heme, but an iron center, but it contains a copper center. So the copper center in this case is the active site in the protein that acts as a storage for electrons. Electrons get in and they get out. And here's a picture of the protein. Here you see the backbone of the protein. It's not so large, it's about 14 kilodalton. The copper is here, it's beneath the surface, and it's kept in place by side chains, 4 side chains, or 5 in this case, methionine, a cysteine, there are 4, and 2 histidines. This one is important because if you look from this side here onto the protein, you see this. And this histidine 117 pierces through the surface. And when we saw this for the first time, we thought this histidine could be the important part of the protein structure, where electrons get in and out. And we did several experiments to check that, and we proved that this histidine here is indeed the port of entry and exit for the electrons. I'll show you one picture or one experiment of the many that we performed to prove that. Here is this picture, here's the protein. And we took a mixture in which half of the protein was reduced, symbolized here by this white circle, and the other half was oxidized. When these proteins, a reduced one and an oxidized one, may meet, they can exchange an electron if they like. And that actually happens. And so we investigated that exchange reaction from here to there. So this is a sort of symbolic presentation. 2 proteins come together and they may exchange an electron here, from here to there, or from there to there. Now the disadvantages of this type of experiments, you can't keep the proteins fixed. That's what you would really like to do and study them in detail. So what we did is we fixed the proteins, a dimer. And we put a link here between these 2 parts of the protein. And we first made the following link. We just put 2 cysteines, which had a sulfur exposed, which happened to be there. We connected them by oxidizing them. And you get, if you do the crystal structure, you get this sort of construct, like you see here. The speed by which electrons travel from one side to the other is only 5 per second. We could measure that by NMR. If you're interested, at the end of the talk, I have a few slides to demonstrate how we did this with NMR. It's very slow. Then one of the students had a bright idea, and he said, listen, this link here is so tight that the proteins cannot rotate opposites to each other. But if you connect them here with a linker that gives them a bit more space, then the crystal structure shows that this is the preferred conformation. Now the electron transfer, intramolecular electron transfer, is 10 to the 5th per second. So it's an enormous change in the rate. And the reason is the following. Here are the numbers. I don't dwell upon these now. But this is the structure if you look at the details. Here is one protein, here is the other, here is a copper, here is the other copper, and here are two water molecules. Here are histidine 117 and 117. You see them here also. And the electrons can travel through this path. So there now is an electron transfer path. And that is the reason that the electrons can jump so quickly. Is it possible to play with this electron transfer path? The answer is yes. What we did is we made a protein where this histidine 117 was engineered out of the way. So you create a gap. Surprisingly enough, the protein keeps its structure and is stable. So it's this one. You get a gap. The gap fills up with water. And the protein, instead of being blue, becomes green. And then you can play the following games. Here's the protein with the gap. It is green. Here is the same protein, but we have added a little bit of imidazole. That is very much like the original imidazole that was in place in the natural protein. And lo and behold, this one fills the gap, and you get the blue protein back that you also get from nature. The only difference is that if you reduce this, you make this copper 1 instead of copper 2, this one falls out and you end up with this protein. So you cannot study the electron transfer of the protein when this one is in place in the gap. That's unfortunate, but we have other means to check the electron transfer. Now, what other games can you play then? If you know that this one goes into the gap here, then you take this molecule. Our organic chemistry friends synthesized it. And then you can react it with this protein, and you get this back. The linker here now connects the two coppers, and you get the dimer, and this is the crystal structure of the protein. And the two coppers now, in principle, can communicate by means of this linker. With NMR, it's not possible to study the mixture of reduced and oxidized because, as I said, if you reduce it, the linker falls out. So you have to use another technique. We used EPR. And EPR is able to measure the interaction between this copper and this copper. Only is not as sensitive as the NMR. But here you can see what happens. We have designed a couple of linkers, this time with 6 rings in imidase at pyridine. The pyridine does the trick just as well as the imidazole. And now look what happens. We have here the green protein without anything. There is water in the gap. This, if we add this one, we get this EPR spectrum. This is very reminiscent of the natural EPR spectrum. I don't go into the details. I only show you this to illustrate what happens if you add this linker. This linker is not very conductive because it has here CH2 bridges, so there's not very much happening. But if you add this linker with here a double bond and here a double bond, you get a conjugated system. And the conduction now is so strong that you see the effect of the interaction between the coppers on the EPR spectrum. This is clearly different from here. And we can simulate that, and for the technically oriented people in the audience, I can tell that the exchange interaction between the two coppers is something like 780 megahertz. In terms of electron transfer rate, if you would be able to measure the rate, would be an enormous rate, thanks to the fact that we have a conjugated pi system. Now, I would like to switch here and focus on single molecule experiments. And the picture that most characteristically summarizes the sort of experiment that we do is shown in the next slide. Here you see a picture, an etching by Antonio Tempesta, 1606. It is visible in the Rijksmuseum, the National Museum in Amsterdam. And it depicts the science from antiquity, where we have here the god of war, Mars, who fell in love with the wife of his brother, Vulcanus. And here is the wife, is the goddess Venus. And Vulcanus was warned that something happened, and so he went down and made a fine mesh and threw it over this pair, and then they couldn't move, and everybody could study in detail what was happening. That's exactly what we want. We want to freeze a single pair of reactants and then let them have a look at them precisely on what is happening. So this is sort of the PhD student that is looking. Now there is another parallel which is interesting. In antiquity there were 7 planets known, but there were also 7 metals known. And so there was a correspondence set up between the gods, between the metals and the planets. Mars was connected with iron and Venus with copper. And these are just the metals that are most frequently observed in biological redox chemistry. So that makes it very interesting. And we look, in our case, at the reaction between copper and iron. So the copper is connected in azurin, and this is when the copper is in the copper 1 state, it's reduced. This is iron 3+. We do it by adding ferro and ferricyanide. This is the oxidized iron. It takes an electron from the azurin, becomes oxidized. The copper protein becomes blue and the iron becomes reduced. Now the big question is, how do we how do we observe this reaction, especially when we go down to single molecules? Here is the situation of the protein. Copper 1 is colorless. It's reduced, and when you oxidize it, it becomes blue. So it's a simple question. How do we observe that? Well, measure the absorption. If we see that there is an absorption of the blue protein, means a red absorption band. If we see absorption in the red, and we see the absorption change, we know that the reaction has taken place. So, what's the problem? The problem is very simple. If you fire a shot of, say, 1 million photons onto a single molecule, and it absorbs 1 photon, you have to measure the effect of the reaction with an accuracy better than 1 in a million. That means that you have to do the measurement for an awfully long time, and practically impossible. Is there an alternative? Yes, there is an alternative, and that is, do you look at fluorescence? fluorescence is a process by which a photon is emitted, but there is no background in principle, or you can reduce the background as much as you can. Detecting a single photon is possible with present-day technology. So we should change to fluorescence. But here there is a problem. Azurine does not fluoresce. Okay, the next step is make it fluorescent. So we put a fluorescent tag onto the protein. And that is shown in the next slide. Here we have the protein. Here is the fluorescent molecule. And this is what we thought would happen. If the molecule is reduced, there is a lot of fluorescence. If it becomes oxidized, there is an absorption band around 600 nanometers. And the fluorescence is absorbed by the copper. So you see a drop in the fluorescence. The first time when we proposed this to the National Science Foundation in a proposal, there were 3 referees. And they all said, we don't believe this. Now, fortunately, we had 3 weeks to prepare an answer. And in the meantime, we had started an experiment. And this was the outcome. You see it here. We started with a reduced protein with a lot of light. Then we oxidize it chemically. Then we see the light is down and up and down. So we got our project granted. Now this is of course in solution. But now we want to go down to the single molecule level. And the question is, how do we do that? Here is the setup of the experiment. I need to take a little bit of time to explain this to you. We have here the solution with the iron, and the azurine is immobilized on a glass plate. Now we would like to control the concentration of the iron 2 and the iron 3. And we do this electrochemically. We put 2 electrodes in the solution. One is a reference electrode, the other is a working electrode, and we change the potential. If we change the potential, make it oxidizing, for instance, there is a lot of iron 2 that's taken out of the solution and converted to iron 3. So we oxidize the iron. And the iron, in turn, oxidizes the protein. So by controlling the potential in the solution, we are able to control the concentrations of the reactants. This is how the protein was immobilized. We see here the protein. It has a linker here. It is a bit technical, so those of you who are familiar with this type of immobilization recognize that you have here biotin. There is a protein here that has binding sites for this biotin, and here is another linker that connects it to the glass. And this is polyethylene glycol brush to immobilize to make the surface of the glass friendly to proteins. So this requires some chemistry, but once you have found out how to do it, it's a common technique and it works. So this is what we do. We have here the potentiostat that controls the concentration of the iron 2 and the iron 3, and this is the immobilized azurine, and this is how we do the experiment. We have here a microscope, a Zeiss microscope, and we use that to study the glass slide with the immobilized protein. Here is a laser light coming in through the objective with the dichroic mirror. It excites the molecule, and the light comes out and is going through the dichroic mirror. The dichroic mirror means that some light at a particular wavelength is reflected, but light of a different wavelength is going through. So that is what we do here. The light that's emitted is going through, and it falls on the detector after being focused and passing the pinhole. The pinhole here is the trick for the optics. It's a small gap of about 50 microns. And if you focus the light very exactly onto the pinhole, you get a very clear small part of the solution that is really seen by the detector. If this is the laser light, the waste of the laser, this is a very small part of the solution that is actually seen in the detector. This is, the size of this is about diffraction limited, so it's in the order of a few hundred nanometers. That makes it possible to observe the single molecules. This is what you observe. We have here the immobilized molecules, and we scan the laser across the surface, and we look at the fluorescence. If we have here an oxidizing potential of 300 millivolts, most of the proteins are oxidized, and there is no fluorescence coming out. If we switch after that to a reducing potential, say minus 50 millivolts, all of a sudden we see all these single molecules that are lighting up in fluorescence. And now we can start looking at the kinetics. We look at the single spot and we look at the light that is coming out. So we fix our laser light on a spot and we look at the photons that come out. And this is what we observe. This is a reducing potential. So most of the protein, most of the time it is in the reduced state. Say that it is here. And then, so we are talking here. This is azurine in the reduced state. Then every now and then an iron 3 comes in and it oxidizes the protein, it becomes dark, and you see this. If you go to a slightly more oxidizing potential, then the oxidation of the azurine occurs quicker, and you see that the bright periods become shorter. And if you go further, you go very short, and the bright periods become very short, and the dark periods become very long. The question is, how do we analyze this? Now, what we did is we made a list of the times, and we plotted these as a function of time. So what you see in the next slide is, here in this case, all the experiments were done at 100 millivolts. So it's basically this type of traces that we observed. And we looked at many molecules. Sometimes you see this here, sometimes you see this, sometimes this, sometimes this. So what you see here is the behavior of the dark and the bright times as a function of time. And you see a couple of behaviors that are different. There is one here where you see no variation. Here you see that the bright time is long and all of a sudden becomes short, while at the same time the dark time becomes long. We call this anti-correlated. One becomes shorter, the other longer. And here you see a different picture. You see here steady times, and all of a sudden they become both longer. So we call this a correlated situation. And here is a situation where one becomes gradually shorter and nothing happens here. This uncorrelated behavior. And there are also traces where we see no change at all. Okay, now comes the hard part. And now you have to stay awake. I'll put this away. So this is the only part where I will use a few equations. All right? So please stay awake. Here we go. So here we talk about azurine reduced, oxidized, reduced iron converts to reduced azurine and oxidized iron. This picture is a little bit too simple. As Einstein said, you should simplify as much as possible, but not simpler. So this is too simple. What actually happens in solution is this. We have a situation where the two components first have to come together, form a complex, and within the complex, the electron transfers. And then they can dissociate and participate in this equilibrium. So there is an equilibrium between the two free components and the complex. Here also the two free components and the complex. And within the complex, there is an electron transfer reaction possible. So if we want to analyze the behavior of the short and long times, we have to take into account that this parameter may occur. The electron transfer within the protein in the complex is important, and the complex formation here. Now I will look at this because these are just governed by the association rates here and dissociation rates, which are in the order of 10 to the 4th to 10 to the 6th per second. Very fast compared to this one, which is in the order of 10 to 100 per second. So I look first to this one here. And this is usually analyzed by this type of equation. The rate is proportional to the effectivity of the electron transfer path that is measured by a sort of electronic matrix element. And here an exponent where we have the driving force, the amount of free energy that is freed in the reaction, and some kind of activation barrier energy. I will not talk about the lambda, but only about the free energy change and the effectivity of the electron transfer path. Okay, so we will look into these two parameters and see if we can recognize variations in these parameters in the characteristics of the traces that I just showed. Here is the picture of the iron cyanide, the ferri and the ferro. They give electrons to the copper here. And here is the behavior that I would like to analyze. The two change, but they change anti-correlated. One goes up, the other goes down, the times. It means that the reaction rate, the forward and the backward, go either up and down. So if we have this reaction equation, then we have to realize that the change in the forward and the change in the free energy in one reaction goes like this, but the other reaction back goes like this. So if this gap changes, one goes faster and the other goes slower. And that is exactly what we see here. One goes slower and the other goes faster. And that is related to the driving force or the free energy. It means that the reduction potential of one of the partners, probably of the azurine, all of a sudden changes. And that is possible, for instance, when at one particular moment a proton jumps onto the protein and changes the total net charge on the protein. The other one that we want to analyze is the effect of the effectivity of the electron transfer path. What is an electron transfer path? Well, I gave you a couple of examples with these linkers between the two coppers, but here we have an example where we have sort of arbitrarily tried to map, by theoretical calculations, the map between a nitrogen atom here and the copper here. If you put an electron here, how would it travel to the copper? You can do calculations. And what you see here is the path occurs along a number of covalent bonds here and ends up with the copper. Here is an alternative path in yellow. So the path here runs mostly through the structure, the structural elements of the protein. Sometimes the electron jumps if there is a gap, but most of the time it's conducted by the covalent bonds. This path is very sensitive to the details of the structure. If one of the covalent bonds make a flip, which a chemist is very well familiar with, the effectivity of the path may change. All right, so let's have a look now here. What we think is happening here, because the times change in parallel, that this factor, changes in this factor, explains why these changes occur. That is symbolized here. We have here the iron 3 and iron 2 that associate at the surface. The electron transfer takes place back and forth, and all of a sudden the effectivity of the path changes, for instance, by small flips in the transfer path, and the effectivity changes tremendously. And that is what we see here. And finally, we have this behavior where one of the paths changes its effectivity and the other stays the same. And we think that that may be due to these two. It is possible to consider that the iron 3 occurs, associates at one position, and the iron 2 at a slightly different position, and that the position changes a bit because of small variations in time on the surface. So, summarizing, we have various behaviors. We have no change. That means that we look at the situation where the protein and the iron are behaving in the same manner. Then we have the correlated change, means that the pathway changes. The anti-correlated means that the driving force or the reduction potential of one of the partners changes. And the uncorrelated behavior may have to do with variations in the structure of the complex. What does that teach us about the natural electron transfer process between two proteins? There is an important difference. This situation is artificial in the sense that we have taken the protein and added just a reductant. In nature, the partners are exactly designed for each other. That means that variations in the complex structure is probably much less important than in the case that we have studied here. So this will probably be of very little importance. And then we see that the most variation comes from variations in the path. So if we talk about electron transfer in proteins, in natural processes, we now have shown that there may be variations on time scale of seconds or hundreds of seconds. They may be due to changes in the electron transfer path, and these are the most important variations that may occur in the natural electron transfer processes that are responsible for our energy. So we can now start looking to next experiments to investigate what sort of changes in the electron transfer path are important and what kind of effect they may have on the biology of our cells. Now, I assume that I have eaten up my time now. Yeah. So let me finish. I was going to tell a little bit about optical antennas, but let me go on to mentioning the people that have contributed to this work. In Leiden, there is a long history of people that have collaborated on this work. I like to pay a special attention to this person, Professor Gilardi, who was there when we tried to make the first contacts or assemblies of proteins, and he is now a master of assembling all sorts of protein domains into new active protein compositions. These people here were involved in the changing of the making mutants of the protein. Marcellus Ubbink is now professor of biochemistry in Leiden, and these people here were involved in the first single molecule experiments. I've talked about azurin, but we have also looked at a couple of enzymes where we could just study the electron transfer between different centers in the protein. These are my colleagues, Professor Aertsma and Professor Orit. Aertsma was involved in the single molecule proteins. With Orit and these two students, we have been involved in the experiments on the azurin and the iron. Professor Huber was involved with the EPR, and in the organic chemistry department, the linkers were synthesized, and the people here in the hospital were very helpful in analyzing our first labeled protein constructs. These people taught us how to do single molecule experiments, and there are a couple of colleagues here in Italy which collaborated with on constructs where we did biosensor experiments, experiments on labeled azurin, or azurin with modified histidine 117. These people collaborated on the fluorescence, and Rossi worked on some of the crystallography. These people were very helpful with helping us solve the crystal structures, were indelible for the work. With Myrna, we did single molecule experiments on one of our enzymes. Alan Hill was the person who introduced me to the biochemistry field, and with Jason Davis in Oxford, we have collaborated on electrochemical experiments, and with Chris Dennison, who's now professor in Newcastle, we have collaborated on the mutants of azurin and of a number of enzymes. The support that we have received, I should also mention the EU here and here, the university, the Technical Science Foundation, NATO, the Dutch Science Foundation, and the Valley Foundation. Thank you very much for your attention.